Electromotive force. We have seen that an electric field is needed to maintain a current in a conductor. When this electric current passes through a resistor, it dissipates energy which is transformed into heat. Thus, to sustain a current in a conductor, some source of energy is needed so that it could continuously supply power equal to that which is dissipated as heat in the resistor. The strength of such a source is known as electromotive force. Usually, the potential difference that exists between the two terminals of a battery or any source of electrical energy when it is not connected to any external circuit is called its electromotive force. Simply read the EMF and it's represented by E. As charges pass through a source of electrical energy, that is, a cell or a battery, work is done on them. The electromotive force may be defined as the work done per coulomb on the charge. The EMF of an automobile storage battery is 12 volt, which means that 12 joules of work is done on each coulomb of charge that passes through the battery. In the case of a battery, chemical energy is converted into electrical energy. By means of the work done on the charge is transferred through it. In a generator, mechanical energy is converted into electrical energy, and in a thermocouple, heat energy is converted into electrical energy, and so on. The EMF of an electrical source bears a relationship to its power output analog to that of applied force to mechanical power in a machine, which is the reason of its name. Let us consider a simple circuit in which a resistance R is connected by leads of negligible resistance to the terminal of a battery. A current I will flow through the resistor in a direction from A to B, the potential VA being higher than the potential VB. The same current will flow through the battery from its negative terminal to the positive terminal. The battery is made of some electrolyte and electrodes for the production of EMF, and hence when this current flows the battery, it encounters some resistance by the electrolyte present between its two electrodes. This resistance is known as the internal resistance of the battery. Thus, the current in the circuit from Ohm's law is given by the relation I is equal to E over R plus small r, where R is the internal resistance. E is equal to IR plus I small r. Here, IR is the voltage to drive the current I through the external resistor R, and IR is lost voltage driving current I through the internal resistance of the battery, denoting IR. The potential difference between the two terminals of the battery by V we have V is equal to E is equal to V is equal to E minus IR. This shows that the potential difference between the terminals of a battery drops when it delivers a current. However, when no current is drawn, there is no potential drops across the internal resistance, so that the terminal potential difference is equal to its EMF, that is V is equal to E. In effect, we can say that the internal resistance of a battery governs the maximum current it can supply.